Silk is a new quantum programming language designed to abstract from low-level implementation details of quantum algorithms. In contrast to existing quantum languages, Silk supports a descriptive view on quantum algorithms that expresses the high-level intent of the programmer. As a consequence, Silk algorithms are significantly shorter and simpler, less error-prone, and modify the program's quantum state according to an intuitive semantics that follows the laws of quantum physics. Silk's key technical novelty is a quantum type system that captures important aspects of quantum computation and enables safe automatic uncomputation, a fundamental challenge in existing quantum languages. Silk's development environment enforces static safety and even includes a simulator, so check it out.
Rule-based hardware description languages promote modular decompositions that allow you to derive top-level guarantees by reasoning separately about different parts of the design. Consider two rules forming the two halves of an arithmetic pipeline. The traditional semantics of this system is defined as the execution of F1 and F2 in any order. Considering rules one by one, we can show that an implementation verifies its functional spec. Here, the nth element of the output FIFO should be F2 of F1 of the nth element of the input FIFO. However, the one-rule-at-a-time semantics does not allow us to assert performance properties, such as it takes exactly 2 cycles to produce each output. We introduce a new semantics that refines the one-rule-at-a-time semantics thanks to a user-specified rule schedule together with a dynamic dependency tracking. Our semantics is deterministic and allows us to state and prove performance properties. We show in Cox that our semantics is a refinement of the traditional one, and we develop a compiler to circuits proven to be correct with respect to our semantics.
Chip design today faces a severe redundancy problem. There are many tools from different vendors, all with separate proprietary language frontends. At the same time, languages are complex, and their vague standards have proven extremely hard to implement. Even worse, it is challenging for novel languages to hook into this flow. We propose LHD as an IR for chip design. It allows us to have a single frontend for System Verilog and VHDL that we can get right once, and novel languages can target it directly. As part of LHD, we propose a lowering of the behavioral semantics in System Verilog and VHDL to an unambiguous representation. Vendor tools become simpler as they have to ingest only one IR and can produce LHD again. LHD is a multi-level IR. The behavioral level is easy to lower to from HDLs, the structural level is easy for synthesizers to ingest, and the netlist level captures synthesized designs. To find out more on how we cover the entire chip design flow, come to the LHD Talk.
Have you heard of quantum programming language that operate on emerging quantum machines? Have you heard of differentiable programming language that support next generation machine learning applications? This talk is about happy marriage of both, differentiable quantum programming languages. However, this is not just a brain teaser, but with strong practical motivations. With the establishment of quantum supremacy, we now have quantum machines that we can barely match with classical computation power. One promising application is the classically parameterized variational quantum circuits, whose training requires gradient computation that is infeasible for classical computing. Thus, using quantum programs to compute the gradients of quantum programs is critical for the scalability of gradient-based quantum applications. Designing differentiable quantum programming, however, will face conceptual challenges from the very beginning. Come to our talk and check out how we address them. Our findings might also find hints about unifying differentiable and probabilistic programs.